Welcome to this video course. In this lesson, I will show you how to align a full-range system with a subwoofer using linear broadband IRs. We will achieve this by using standard wave editors, specifically Adobe Audition 1.5, in combination with acoustic software developed by Professor Farina. This work is dedicated to his memory for the great contribution he left to science and to our professional field, and to my own life. Thank you, Professor. The webinar is translated into English using AI. The contents covered in other video courses regarding the following general topics are propedeutic, weakness and subjectivity of the phase trace, time domain alignments, full range and subwoofer alignments using linear broadband IRs. Please make sure you have consulted the aforementioned videos first. I have named this method the Metodo Farina Fedele. I say this with all due respect, in pairing my humble name with that of a giant like Professor Farina. It signifies the unification of two separate methods, following extensive discussions with the professor. It combines his exponential sine sweep method, ESS method, for the acquisition and convolution of the IR, with my method of rising points, in the use of the obtained linear broadband IR. After consulting all the previous lessons, you will have understood that the fundamental problem is obtaining measurements with a high SN ratio and without distortion products when using loudspeakers to reproduce test signals, whether it is the installed PA or a classic dodecahedron, depending on the context. Using a dual-channel real-time analyzer with random pink noise to obtain an IR, which is an IFFT, leads to calculation errors. These occur because of the lack of synchronization between the test signal and the measurement, especially during cyclical window transitions centered on the direct sound. This creates uncorrelated noise that is reversed inside the measurement, significantly lowering the SN ratio. Data windows help, but not too much. Using the cyclic pink noise produced with cycles of the same length and synchronized with the measurement windows significantly raises the SN. This occurs because it eliminates most of the previous errors, especially if the measurement and the test signals start and end together. By combining this last condition with the use of a log sweep, we achieve the maximum possible signal-to-noise ratio, as the log sweep inherently provides a superior SN compared to the use of pink noise. The log sweep is one of the most important test signals. With a log sweep, you have a deterministic signal, which guarantees one of the highest SN ratios. You can create and manipulate this signal according to your needs, in terms of duration, frequency content, and more. Obviously, it is the specific application and study purpose that determine which type of signal to use. Let's see how the information emerges depending on the type of method used. Remember that the FFT size used by your analyzer is a predefined sequence of samples. Each of these represents not only an amplitude value, but also a small window of time, according to the SR used. Consequently, it represents the window of time and space through which you investigate the world around you. This is a fundamental intrinsic limit that you must keep firmly in mind when you want to take into account the entire decay of a room. You must ensure, and in acoustic work, for example, the standards themselves mandate it, that ideally, both the duration of the test signal and the measurement window adequately include the entire decay of the room. This is essential if you are interested in studying the room itself, or the interaction of a sound system with it. In fact, for many works, standards require them to be 2 or 3 times the decay of the sound phenomenon you are studying. It is common to raise the SN ratio by averaging measurements. However, this method is not without its limits and trade-offs. The following picture compares the sonographs of 2 IRs. The first comes from a single long sweep of 50 seconds. The second comes from the average of a series of 50 short sweeps of 1 second each. Note how the repetition of the sweep stimuli significantly increases the formation of distortion products. The single long sweep prioritizes analytical accuracy and an extremely high SN, focusing on harmonic and mechanical factors like rub and buzz. On the other hand, a series of short sweeps involves different physical phenomena, such as thermal and transient distortions, where the analytical detail is conditioned by the sweep speed. Each method produces specific results that significantly impact the final linear broadband IRs. Comparing these two methods, we can see that the energy of the decay tail is significantly underestimated at high frequencies when using averaged measurements. Specifically, above 350 Hz, the signal is systematically lower, with a loss exceeding 10 dB around 5 to 6 kHz. This directly impacts the precision of the linear broadband IRs. In this comparison, filtering the IRs at 4 kHz shows how the single sweep provides a linear decay with a dynamic range of 63 dB. In contrast, the average measurement underestimates the reverberant tail energy, resulting in a much lower signal-to-noise ratio of only 43 dB. This directly alters the slope of the decay curve and the estimate of reverberation times. Therefore, when you use a sound system to reproduce a test signal, especially if it is a log sweep and you require a sustained level, the system produces distortion products. When using common dual-channel FFT analyzers, such as SMART or Systune, you will find these distortion products within your measurement window. This window is typically kept wide to meet various requirements and to achieve a specific frequency resolution. However, for certain standards, a noiseless impulse response, without any distortion products, is mandatory. Cutting them out through editing is certainly an option, but doing so inevitably reduces the frequency resolution that you originally needed to maintain. For professional acoustic applications, which often involve long decay times, I do not use dual-channel FFT analyzers, and I do not want an IR that is merely the result of an inverse fast Fourier transform. My approach is to fire only once and directly capture the room impulse response in the time domain. This allows me to transform it using Fourier, Hadamard, or other methods, freely choosing the windows and the time span I require. This is a different path, better suited for interdisciplinary work and more compliant with specific standards. This approach also allows me to apply the deconvolution method using Farina's technique, which I will explain shortly. It enables me to shift the speaker's distortion products into negative time, providing a rear that is truly free of noise and distortion. As I explained in a previous video, it is crucial to avoid pre-ringing effects when obtaining a linear impulse response. These images are taken from a study by Farina. Specifically, this picture illustrates the pre-ringing effect produced by deconvolving the test signal directly without it passing through the system under test. Always continuing with Farina, the situation ameliorates significantly if we remove the fade-out. The following figures show the results obtained with exactly the same settings as in the previous case, but with a length of the fade-in set to 0.0 seconds. Fade-in is still 0.1 seconds. Albeit the appearance of the waveform looks the same due to the analog waveform display of Adobe AUDITION. Looking carefully at the digital values, the small squares along the waveform, one now sees that the results are very close to a theoretical Dirac's delta function, and that no pre-ringing or post-ringing are any more significantly present. However, it is not a good idea to remove completely the fade-out. At the end of the sweep, the final value computed could be not zero, and consequently the sound system will be excited with a step function, which spreads a lot of energy all along the spectrum. A solution alternative to removing the fade-out is to continue the sweep up to the Nyquist frequency, 22,050 Hz, in our example, as the sampling rate was 44.1 kHz, and cutting it manually at the latest zero crossing before its abrupt termination. This way, no pulse of sound is generated at the end, and the full bandwidth of the sweep removes almost completely the high-frequency pre-ringing. In some cases, also low frequencies can cause a significant pre-ringing. This is shown easily employing a loopback connection. That is, connecting a wire directly from the output to the input of the sound card. The following figure shows the result of a loopback measurement, employing the same parameters as for the previous example. Fs equals 44,100 Hz, sweep from 22 Hz to 22,050 Hz. 15 seconds long, 0.1 second fade-in, no fade-out. Removing the fade-in does not provide any benefit in this case. So, the way of controlling this type of pre-ringing, due to the analog equipment, is to create a proper time-packing filter and to apply it to the measured IR. The Kirkby inverse filter is computed by inverting the measured impulse response through a three-step process. First, the impulse response is transformed into the frequency domain using a fast Fourier transform. Second, the inverse filter is calculated in the frequency domain by applying a formula that includes a small frequency-dependent regularization parameter to ensure stability. Finally, an inverse fast Fourier transform brings the inverse filter back into the time domain, as shown in the provided waveform in the frequency-dependent regularization plot. The room filters any input signal with its unique fingerprint, known as the room impulse response. Think of the signal and the RIR as wave and TXT files. The process can be explained with a time domain convolution or a sum of products between their samples. I have detailed this process with Excel in the convolution videos on my YouTube channel. The IR is hidden within the output signal, and we must extract it. The recorded output signal, YT, also contains noise and distortion products, appearing here as harmonics of the fundamental. To extract a noiseless RIR, we must simultaneously remove these artifacts. To eliminate the artifacts produced by the log sweep, we create its inverse filter. This consists of a time-reversed and re-equalized version of the original signal. From now on, we will refer to the log sweep and its inverse filter as ESS and inverse ESS. The convolution of these two signals results in a delta Dirac. Therefore, X of t convoluted with C of t equals the delta Dirac that is equal to 1. Follow these simple steps with me. We know that xt convoluted with zt equals the delta Dirac, which represents the value of 1. We also know that yt is the result of xt convoluted with ht. By combining these equations and convoluting the recorded signal yt directly with the inverse filter zt, we effectively eliminate xt and zt. What remains is ht, the noiseless room impulse response. Ultimately, this process allows us to obtain high-quality IRs. As mentioned, this process shifts the distortion products into negative time, appearing before the main peak. Now you can appropriately edit the IR. Here is an analytical visualization of the distortion products distribution. The last impulse response is the linear one, while the preceding ones are the harmonic distortion products of various orders. These components appear separated in time, identifying the first, second, third, and fifth harmonic orders. This is the usual setup that is going to be measured and aligned, well known as the protagonist of all my recent videos. It is already known that the top is delayed by default by 20 milliseconds to allow for easy data reading, and that for a correct alignment, about 20.5 to 21 milliseconds are needed, plus a polarity inversion. Now, let's see the method in action with Adobe Audition 1.5. Make sure you have downloaded the software and Professor Farina's plugins from my drive. These versions were optimized by the professor himself. Ensure you have copied the modules into the software's main installation directory. These plugins are fully functional, though they may occasionally crash at random, requiring a program restart. Don't worry, you won't lose your work. Simply restart the application. If correctly installed and activated in the settings, you will see the active plugins in the top right of the toolbar, highlighted as soon as you load a file in Edit View. In Options, ensure you have correctly configured the audio device and its respective playback and recording channels. Make sure the devices and channels you are using are also activated for Edit View. Now, let's open the first of Professor Farina's plugins from the Aurora Plugins suite. Navigate to Generate in the toolbar and open the Aurora Sine Sweep Generator. Typically, these plugins are ready for most common applications by default. In this module, you can select the type and characteristics of the test signal. For this case, we will generate a 14-second ESS. You can adjust the parameters shown according to your specific needs. We generate a mono signal, which appears in the left panel of the editor view. A message will then appear informing you that the inverse filter has been automatically generated and temporarily saved to the Windows clipboard. In Edit, we select Paste to New to create the INV ESS file. In this case, I am currently viewing the spectrum of the generated ESS. Now, select and visualize the inverse ESS as well. Now, assuming you are familiar with the software, add the ESS to the multitrack view and arm a channel for recording. When pressing play, the ESS reproduced by the top is recorded. In the Edit view on the right, the noise and a hint of distortion products can be seen to the left of the fundamental. In the same way, the contribution of the subwoofer is recorded. The recorded signal can be amplified or normalized using the specific tools in Audition. This helps to better visualize the waveform, provided the signal-to-noise ratio is not too poor. Now, the impulse response must be extracted from the raw recordings. Open the inverse ESS in Edit view and select Copy to save it to the clipboard. We can then proceed to the next convolution step. Open the top trace in Edit view and select it entirely. Invoke the Convolve with Clipboard plugin and keep the default settings, perhaps just checking the option Full Auto Range and Remove DC. The plugin is now ready for the convolution with the inverse ESS already stored in the clipboard. Here is the IR of the top. By zooming in, the distortion products are now visible in negative time. Repeat the entire procedure to obtain the subwoofer IR, which can also be normalized. It is recommended to perform normalization on the resulting impulse responses rather than on the raw recordings. Once the correct linear broadband IR responses for both systems have been obtained and potentially edited, they can be aligned by applying the rising points method. We will be very fast, as you will see. First of all, you can remove all the other traces once they are saved, and then export the IR of the top and the subwoofer into multitrack view. Now, we can use the various zoom tools provided by the software to identify the two rising points of the top and the sub. Then, simply use the mouse to select the area that separates them. By right-clicking the gray box at the bottom, you can see the values for the selected area in both samples and milliseconds. In this case, the selection is about 21 milliseconds, which is exactly the delay needed to sync the two systems. For more precision, you could also calculate the exact value using the number of samples. The alignment is now finished. However, running both systems together would cause a cancellation. This is because a final polarity inversion, as you know, is still required to complete the setup. In conclusion, this work proves that linear broadband impulse responses can effectively align full-range systems and subwoofers, moving beyond traditional phase trace methods. By using common wave editors and integrating Professor Farina's ESS method with the rising points method, we unlock new uses for noiseless IRs, including distortion analysis and ISO 3382 acoustic calculations, and many other advanced applications I teach in my courses of applied acoustics for sound reinforcement. This entire process is performed within Adobe Audition 1.5 using Professor Farina's professional tools. Thank you, Professor, for everything you have given me.